Hi everyone, and welcome to the last video of section 1 on deep feed-forward networks. So basically we will finalize this section by an example. So last time we discussed an example of backpropagation using only a single example as an input, right? So you have a single input vector, a single input training example. Now here we'll assume, we'll consider the case where you have a mini batch, right? And these many batch means a group of examples. So the input is a group of examples, and we calculate backpropagation. We calculate the update of the weight parameters corresponding to that group of examples simultaneously as one group. So in backpropagation, basically we will see how to compute the gradient with respect to the weight parameters as a result of the loss of that group of examples. So we forward propagate the group of examples, then we compute the loss, then we compute the sensitivity of that average loss over that whole group of examples with respect to every weight parameter. Now, many batches are usually used in optimization problems for deep learning, and specifically stochastic gradient descent methods, and we'll discuss that later in the third section of this course on optimization methods, which corresponds to chapter 8 in the reference book. So now X is a matrix, right? So it has, so that matrix has you can think of it as multiple rows, multiple columns, or multiple rows, each column corresponding to one example, one training example, right? And then the rows, different examples, right? So every example is a multi-dimensional vector, right, corresponding to the input neurons of that example, and then you have multiple of these, right? So now the first layer transformation, so let's assume we just have a single hidden layer for simplicity, and let's assume we also have no bias, again for simplicity, right? So now this the linear transformation in the first layer will now become a matrix multiplication. You multiply the X matrix containing all the vectors, right, with the W matrix, basically the weights, so that you get another matrix, and that matrix has the pre-nonlinearity of all corresponding to all the examples, right? So you have the pre-nonlinearity neurons of all the examples arranged as a matrix, right? So again, this XW, that's a matrix, right, containing the pre-nonlinearity of all the examples, right? And then you apply ReLU, which is, so in that example we are assuming we have, in that example we are going through, we are assuming we have ReLU, so max 0 and that matrix, right? So basically all the negative elements of that matrix of the pre-nonlinearity values will be zeroed out. All the negative values will be zeroed out. And then you obtain H, which is the output. So this is a matrix of the output neurons after the first layer of every example in the mini batch. And then H is multiplied by W2, which is the weight transformation of the second and final layer, because we have only a single hidden layer. And then you apply the cost, J, and the cost is divided into a J maximum likelihood estimator, which is the cross entropy cost after applying softmax, and then a regularization term with the regularization coefficient. And the regularizer here is what we call an L2 regularizer. So basically it's a penalty of the square of the sum of the square values of all the weight parameters. Okay, we'll discuss that in more detail later, L2 regularization, what it does in the next section, but the main intuition you can think of as it prefers or it biases the solution towards solutions with smaller weights, smaller in magnitude. That's why we have the square. Now let's see how the computational graph works. right? So here you have x, and then w1, and then you have an operation here, matrix multiplication, right? And that operation comes with a definition of the backpropagation method, right? So remember, we said in the TensorFlow approach, or the symbol-to-symbol differentiation approach, when you define a new operation, it comes with its backpropagation method. You have to define how to backpropagate this operation. And then you get U1 after the matrix multiplication, then you apply ReLU, that's another operation. You get a new vertex. So notice that the pre-nonlinearity and the after nonlinearity are different nodes in the computational graph. And then H is multiplied by W2. And then you have the Y, which is the training label. With W2, you apply the cost function, the cross entropy cost function. Now, the gradient with respect to Wi of the regularization term, this is simple, right? So this is the regularization term is just a quadratic function. Computing the gradient with respect to any parameter in it is a straightforward operation. So let's say we start. So let's see how to compute the gradient of the cost, the cross entropy cost, right? So regularization is straightforward. Let's take the second component, the cross entropy cost. Let's see how we compute the gradient with respect to every wave parameter. So we start by having a gradient on the unnormalized log probabilities, which is the output neurons, right? We start by having the gradient of the cost with respect to the output neurons, the unnormalized log probabilities provided by the cross entropy. So this gradient is provided by this G here, right? Is provided by the cross entropy operation, meaning cross entropy is just another operation, like matrix multiplication is an operation and ReLU is an operation. We compute that gradient is provided by backpropagating the cross entropy operation, right? And then we backpropagate this G, right? So the next step is here. I want to backpropagate the G from U2 to H and W2. To find the gradient with respect to W2, we already have a gradient of the regularizer with respect to W2. That's why we say here that we add, right? So we add to the existing gradient of the regularizer, right? And we add to it H transpose G, right? Why? Because H transpose is basically the gradient of U2 with respect to W2. How do we know that? This is provided using the backpropagation rule for the second argument of matrix multiplication, meaning that matrix multiplication comes with a backpropagation rule for its first argument and the backpropagation rule for its second argument. The backpropagation rule for the second argument says that you have H transpose, right? And H transpose is multiplied by whatever gradient you have of the output with respect to the output, which is U2 here. So G is the gradient with respect to U2. And then you multiply it by H transpose. Then you get the gradient with respect to W2, right? So here we computed the gradient of the final output with respect to all the parameters in W2. Then we want to backpropagate that gradient so that we can compute it for earlier layers, right? So we want to compute it for W1 as well, right? So the gradient with respect to H of the cost is G W2 transpose, right? How do we know that? This is using the backpropagation rule for the first argument of matrix multiplication, right? And then ReLU, so we discussed before, ReLU, the backpropagation of ReLU does what? ReLU is a function that looks like this, right? In this region, the gradient is 1. In this region, the gradient is 0. The derivative is 0. So ReLU.B_prop, what it does is that it zeroes out the elements corresponding to negative entries of U1. Now that's really important, right? Because that means what? That means that in order to backpropagate, I have to know the values of the pre-nonlinearity, right? So that's why forward propagation is a necessary condition, right? So I need to store all the pre-nonlinearity values, right, in memory before I start computing the backpropagation. And corresponding to the negative entries, ReLU would just bprop of ReLU would just zero out these elements, right? Zero out the gradient of these elements, right? So I have the gradient with respect to H here, and then I process that gradient by zeroing out all the elements with indices corresponding to values of U1 that are negative, right? So I have this gradient here, I look at U1, all the elements in U1 that are negative, the corresponding entries, I zero them out in the gradient, okay? And then we add X transpose, so we obtain G bar, right? The new gradient, that's the gradient with respect to U1. Then again, we use the backpropagation method of matrix multiplication for the second argument to compute the gradient with respect to W1. So this G bar, right, will be multiplied by X transpose and then added to whatever gradient of the regularizer with respect to W1. So we already have the gradient of the regularizer with respect to W1. We add to it X transpose G bar using, again, bprop of matrix multiplication. And hence we are done, right? So in some special applications, we can be interested as well of the gradient with respect to the input, as we will see in one of the projects on the adversarial machine learning problem. But in general, aside from adversarial machine learning, we don't need to compute the gradient with respect to the inputs, just with respect to the weight parameters. Now the computational cost is dominated by the cost of matrix multiplication, right? Because this is much more costly than addition. Now matrix, this is actually the reason why you see, one of the reasons why you see GPUs very useful in deep learning training, because GPUs are graphical processing units, and matrix multiplication is a very common operation in rendering graphics. So all these GPUs were originally designed for parallelizing matrix multiplications. And since the computational cost of deep learning training is dominated by matrix multiplication, the hardware that was specifically designed for parallelizing matrix multiplication turned out to be very useful. So that's one of the reasons why you see GPUs speeding up training of deep learning algorithms. Now the memory cost, aside from the memory cost that happens during backpropagation, right? And the reason is that the memory cost while running backpropagation, maybe after I'm done with a layer, I can remove all the gradients with respect to that layer and then proceed, right? So I can remove from memory. But the memory cost corresponding to storing all the pre-nonlinearity like U1 here, right? That cost is I cannot avoid it because I have to forward propagate the whole network. And I have to store all the values of the pre-nonlinearities, right? In order to start running backpropagation and construct the computational graph corresponding to backpropagation, right? Because of that operation here, right? So I have to have the gradient is different, corresponding to different regions of the nonlinear activation. So I have to have all the pre-nonlinearity values, and that dominates the memory cost. Right, especially if you have a mini batch, then let's say I have m examples in the mini batch, and I have nh hidden units in the whole network, then the memory cost will scale with m times nh. Sounds good. So that was the conclusion of section 1. From next time, we'll start discussing the second section on regularization.